Hello, I am back with my message of unity and harmony. And we're going to take a gander at the source code of Libsodium, which is a fork of NaCl, which is, I think, the better known library. I don't know what's up with Libsodium, but it's a crypto library based on NaCl. Maybe we can do... Should I use NaCl or Libsodium? Libsodium has everything that NaCl has. I think Libsodium is used more. Maybe it is used more. Still relevant and maintained. The NaCl site was last updated in 2016. Okay, so maybe NaCl is donezo. Libsodium was updated several months ago. And for some reason, the implementation lib I'm using, recommended for Dart by Libsodium, has recently decided to depreciate. I think they mean deprecate. To depreciate password hashing for undocumented reasons. All right, let's ask Gemini. I'm writing a super important cryptography app. Should I use NaCl or Libsodium or some other library? Okay, I guess NaCl is not maintained. So Gemini is recommending Libsodium. Is actively maintained, improved usability, is a far more user-friendly API, wider functionality, etc. Let's find out the NaCl library. So this is Daniel Bernstein. Steen or Stein? Bernstein? Let's ask Gemini again. Is this pronounced Bernstein or Bernstein? A bit of a toss-up. Traditionally, Bernstein. Some, particularly those with a German background or familiar with the original language, might pronounce it Stein. If unsure, use Bernstein. Okay, I don't know. Sorry, Daniel J. I'm not sure. I don't remember what to call you. I hope I don't get it too wrong. So that's NaCl, and then the Libsodium fork just seems like it's some dude's GitHub repo. It's an API compatible fork of reference NaCl created in 2013. But the thing, so to me, the thing about NaCl that's was, I think, Daniel Bernstein is a famous cryptographer. I don't know if he's famous as a programmer, but certainly as a mathematician and cryptographer who's well known. So that adds a little bit of authority to the library. And I don't know who the forker is, and that's one of the considerations when it comes to crypto libraries. Frank Dennis. I think this is the main Libsodium thing, right? Introduction, Libsodium. I know that this doc links to the this GitHub repo. So who is Frank Dennis? He may be another famous dude, I don't know. There's a blog, oof.net, an introduction to CDNs, Jedi/Sector 1. I mean, how do we know that this is not another of the of that. Was it the XN or the backdoor that we saw? I don't know. All right, so we'll assume this guy has not inserted a secret backdoor in Libsodium, and let's check it out. We've got some financial backers, including the number pi, which has done a lot of great stuff for an irrational number. You don't see a lot of numbers on GitHub donating to people, but pi is really out there. Okay, so we have source. I'm going to guess everything is in source. What else? What is even the other possibilities? We have regen MSVC. I'm going to guess that's Microsoft Visual Studio Code. M4 is translations. There's some packaging stuff like .NET. There's building stuff and CI stuff. So it has to be in source. It must be. And it's small, I think. So we have EAD. So that's authenticated crypto. We have auth. Box. I'm not sure. This might be related to like SBox type stuff. A key derivation function. KX is probably key expansion, crypto hash, generic hash. And we should look at crypto core, crypto stream, crypto verify. So sign and verify are asymmetric crypto. We have some include stuff. It may be that all the headers are include, which is not my favorite way of organizing, because then I have to jump back and forth between different folders to figure out which headers are what. We have codecs and core in the sodium. What is codec? We have bin to hex. So I guess binary to hex. It's just hex encoding. Hex to bin. Does that count as a codec? B64 car 2 byte. Okay, so this is just encoding and decoding strings, essentially. Here's core. I'm going to guess core is maybe like kind of like a where you hang the like command line-y stuff, if there's a command line tool. We have runtime get CPU features. So we have sodium init, and we're entering some critical section. And we are going to pick a bunch of implementations. So Argon 2, pick best implementation, Blake 2B. And so these things might matter a lot, maybe for like constrained environments like embedded devices, where maybe you might have something like embed TLS, which is going to be like a smaller implementation of TLS as opposed to something like OpenSSL, which is the kind of standard implementation. And here's the crit init thing defined. It's going to do some interlocked compare exchange with the initialized stuff and check. I don't really know what this is. Checking if it's equal to 1, etc., etc. Okay. So this is not the most important. I think I forgot to start my 30-minute timer. And let's march along. So the Libsodium, oh, that's where we were. Okay. So auth has HMAX SHA-256, HMAX SHA-512, and a crypto auth file out here. Let's see what this crypto auth is about. We've got crypto auth bytes, which is going to just return this crypto auth bytes thing. And it's essentially a getter. Get the primitives. Auth verify. We're using a lot of unsigned cars. So these are not even like smart pointers. They are const, which is nicer than not being const. But these are just raw pointers. And we're passing them into the crypto functions, which is maybe what you want. That's how you get, I guess, speed and performance. Crypto box. Wait, we might come back to auth, but auth I think is mainly like combinations and concatenations of things we're going to see elsewhere. We have CryptoBox Easy, CryptoBox Seal. Maybe a CryptoBox is like a container for crypttext. We have seed bytes, before n bytes, 0 bytes. We have CryptoBox key pair. You pass in a PK, maybe private key, an SK, I don't know, maybe signing key, and a seed. And we're going to return a CryptoBox curve 25519 X salsa 20 poly 1305 seed key pair. Okay. Let's look up Libsodium CryptoBox. Sealed boxes. Sealed boxes are designed to anonymously send messages to a recipient given their public key. Okay, so here's how it's called. Recipient creates a long-term key pair. Okay, so SK is, I guess, secret bytes. PK is public bytes. So we create this this public key and the secret key, and we pass that to CryptoBox key pair. And then anonymous sender encrypts a message using an ephemeral key pair and the recipient's public key. So we create a thing for ciphertext, which is empty. Oh, I guess we're populating this. And then I guess that's an out parameter in the first argument, maybe. And then we pass in the message length and the recipient's public key. And then when you are the recipient, we're going to create a new message of message length. And we're going to call open. And I guess it'll be filled into decrypted. We're going to pass in the ciphertext, the ciphertext length, and the recipient's public key, and the recipient's secret key. And we're passing in length as opposed to, I'm just thinking about this from like a easy to use and safety perspective. It seems like the ideal case would be if you couldn't possibly get this wrong, that somehow it knew exactly how long the message was. And maybe you would sometimes want to only encrypt part of the message, but it seems like fewer things can go wrong if the thing you pass in already has its length associated with it. All right, so that's a crypto box. I'm going to think of it as just again, a combination of crypto primitives and stuff we're going to see elsewhere. So here's crypto core, and we have ED 25519, H Chacha20, H-Salsa20, Salsa ref, and soft AES. I don't know what makes soft AES. Chacha and Salsa, I think, are both DJB things. DJB Salsa is everywhere. Let's try the Wikipedia page. So he is known for a salsa and salsa20 and Chacha20. So salsa and Chacha are stream ciphers. Salsa20, the original cipher, was designed in 2005 and later submitted to the eStream European Union cryptographic validation process. It's a modification. So Chacha is a modification of Salsa20 published in 2008. It uses a new round function that increases the diffusion and increases performance on some architectures. Okay, and here's the salsa stuff. Maybe we'll come back to this. And Aiden is saying, I learned basics of languages like C++, Python, and with that, I go to actual codes in GitHub, and I can't figure it out. What should I begin with? And move on to understand these real-world codes. It's a good question. a lot of times when you're at the beginning of your learning journey, one of the things that I like to say from it's from psychology, specifically the psychology of learning and education, is that what makes an expert isn't so much that they know more than everybody else, which oftentimes they do, but there's a real sense in which experts know what they don't know. So they somehow kind of like have a map of the land, and they know what their competencies are and what their competencies are not. And when you're just starting out, you not only have limited skills, but you also don't know like what all the skills you need are, or like what you're most weak in. And so that's a really difficult place to be in. And I think that's maybe a little bit what you're struggling with. And that's not just for computer science, that's really for anything you start anew in. That's why a lot of times you'll see successful people or even really smart people, they won't want to try new things, because when you try something like fundamentally new, then you're really bad at it for a pretty long time. And people often don't. People who are used to feeling competent don't like to feel like they're bad at something. So I think that what I have found personally is when you're not sure where to start, you kind of just have to realize that like the main problem you're facing is you don't know what you don't know yet. And when you don't know what you don't know, you're never going to find the perfect place to start. You're always going to waste some amount of time and go down the wrong direction. So I guess what I would suggest is to spend some time exploring, and keep learning. So if you know the basics of something like C++ or Python, I would dig deeper into one of those languages. And I wouldn't necessarily go by like what people are excited about. I would kind of go more by what is actually like drawing you to the problem, or to computer science. Because if you can find a way to align your learning with what your actual interests are and what you actually want to spend time doing, then in the medium to long run, that's going to pay off a lot more. So that's my advice. You just got to spend some time doing it. Like be really kind to yourself, not feeling like you don't know what's going on, and just, try to, get used to feeling like you have no idea what's going on, and like be comfortable being uncertain and disoriented, but also look for places where you feel like you're like finally understanding something. Because those are you get kind of these islands where you can build up a scaffolding, and that it's really just about building that scaffolding up over time. But in order for that to make sense, you have to, have spent enough time exploring the stuff where you didn't have a real good foothold, if that makes sense. And I'm realizing that I never set this timer, which is good because I just stopped to talk to the chat for a little bit. So I'm going to reset it for, I think, 25 minutes. And let's plow along. Okay, so these are the crypto algorithms. So Chacha and Salsa are Dan Bernstein stuff. I don't know about this particular curve, ED25519. I don't know if he's associated with that as well. Curve 25519. Yeah. The original curve 25519 paper defined it as a Diffie-Hellman function. Daniel Bernstein has since proposed that the curve 25519 be used for the underlying curve and the name x25519 for the Diffie-Hellman function. It's one of the fastest curves in ECC and not covered by any known patents. It was first released by Daniel Bernstein. Interest began to increase considerably when it was discovered that the NSA had potentially implemented a backdoor into the P256 curve-based dual EC DRBG algorithm. Yeah, I remember that. While not related, suspicious aspects of the NIST's P-curve constants led to concerns that the NSA had chosen values that gave them an advantage in breaking the encryption. Bruce Schneier says, very famous crypto popularizer guy, I no longer trust the constants. I believe the NSA has manipulated them through their relationships with industry. Okay, and we saw in the Bitcoin code, I mentioned that my theory was that one of the reasons Bitcoin chose kind of an oddball curve is because they were concerned about the NSA curves. Or the US curves. I think it's the NSA, right? At any rate, let's look at these implementations. I don't know what soft AES is, but let's take a look. Okay, so we have AES loot. I keep forgetting what loot is. Lookup table. And these are a bunch of, I think these are the AES constants. So here's the AES S box. 0, 0 is 63. That's what? I forget how to do. This doesn't seem to be 63. Yeah, I'm not sure what we're really looking up, but this is something. How many lines is this? 10 to 41. And how big is the S box? So 10, 11, 12, 13, 14, 15. Yeah, I don't know. Okay. All right, so we have the soft AES block. Maybe soft AES is like software AES as opposed to like hardware accelerated. In fact, I'm going to guess that's what it is. There's some stuff about inline assembly. Yeah, I'm guessing this is just software. Let's do just a Google search of this stuff. AES source code. Okay, so here's the S box, and then here's the pre-calculated table. Is this the A5636? Okay, so I don't know what the pre-calculated table is for. Advanced encryption standard. So we have this S box thing and a shift row step and a mixed column step and an add round key. In the sub-byte step, each byte in the state is replaced with this entry in a fixed 8-bit lookup table. So I guess that's what the lookup table is. Something along those lines. All right, some lookup table. I don't see the S boxes here, but maybe, I don't know. Here's salsa ref.c. Maybe this is the reference implementation. Crypto core salsa. We're going to take it. We have an out parameter as the first thing. It's going to give you an unsigned car, and then a bunch of const stuff in K, C. I don't know what K, C is, and then some number of rounds. And we have a bunch of variables, x0 to x15, j0 to j15, and some int I, probably a counter. We'll set j0 to be the same as x0 to this constant. And similarly for J5, J10, etc. And if C is non-null, is C like the existing stream? Let's find the pseudocode. Initial state? The initial state is made of 8 words. 2 words of stream position, 2 words of nonce, essentially additional stream position bits, and 4 fixed words. So I think this is kind of what we just saw. Is that right? So the key, 8 words of key. The key is blue, the nonce is green, and the stream position is red. So do. The constant words spell expand 32-byte K in ASCII. This is an example of nothing up my sleeve number. Okay, so the numbers are not pre-cooked up by the spooks to add a backdoor. The core operation in Salsa20 is a quarter round of ABCD that takes a 4-word input and produces a 4-word output. So we're going to take B, XOR it with A plus D, and then this triple shifty operation. I guess this is like a streaming operation? Well, I don't know. I don't think that's a C++ thing, is it? Maybe it's like a crypto. Let's ask the AIs. In crypto pseudocode, what does mean? The left circular shift. That means that bits are shifted to the left by a specified number of positions, and any bits that are shifted out of the left are reintroduced by the right. Okay, this is circular shifting. Got it. All right, so we're going to take A plus B, circular shift them, I guess, by 7, and then C. Okay, so in each of these operations, we are leaving out 2 things. Here, we're leaving out C and D, and we're assigning it to B. We're XORing it and shifting it and assigning it to B, and so on and so forth. This is kind of a combinatoric flavor. Odd number of rounds apply QR, ABCD, to each of the 4 columns in the 4x4 matrix. And even numbered rounds apply it to each of the 4 rows. So we swap the columns and we swap the rows every other round together. These are called a double round. Great. All right, so now with that, armed with that knowledge, let's consider this. So we are going to call load 32 LE on C plus 0, C plus 4, C plus 8, C plus 12, if C is non-null. Oh, wait, but what is C? That's what we originally were trying to figure out. The stream cipher, right? No, whatever C is. In K, oh, K must be key, of course. C is whatever C is in round. I think this is a stream cipher, so I think C must be whatever the current stream is, or maybe I guess the thing that we're encrypting. All right. So I don't know if load 32 LE is this like add and shift is this shift operation. Although we're not passing in the amount of shift by. This might just be all initializing still. No, we're loading key stuff. We're loading the part of the unencrypted stream, I believe. No, that must be input. So out, in, where's the key? Oh, that's the block out. I don't know. Well, I don't know what C is. Whatever it is, it's a thing. Okay, so here now we have the rotations. So this is all like loading stuff up into the, I guess, the matrix for Neo to operate on. And then here we're actually doing the for loop. These are the rotations. Rotate left, or I guess passing, we're 32 because we're passing in the 32-bit integer. And so we should be alternating left and right, but these are all lefts. And then what? Do we get rot R anywhere? I don't know. But these are certainly rotations. And then we have the store 32LE. And then when we call cryptic course also 20, that's when we call this function. We've got out, in, car K, car C again. And we return 0. Why? I don't know. And we have this thing, output bytes, input bytes, key bytes, const bytes. Oh, I guess const is like a constant, maybe like a nonce. And that's really about it. Why are we only doing rotate left and not right? That I am curious about. See if we can find a rotor. We have rotor 64, rotor 32. Oh, no, we are always rotating left. I was thinking of this thing. What is this? Column round versus row round. Okay, yeah. So I was just confused, as I often am. It's always this left rotation. So that holds up. That's fine. So that's the salsa, like reference implementation. H-Salsa20. I don't know what H-Salsa20 is. What makes it H? I don't know, but there's a ref2. Ref2.c. So this is some like kind of modified version somehow. We've got unsigned 32s now, and we're loading some stuff. We're calling rodl32 as before. I'm not sure. Maybe we can find I don't know if it's got like a hashiness to it. Ask what's the difference between salsa20 and H-Salsa20? Salsa20 is a stream cipher that generates a pseudorandom stream of bits. H-Salsa20, on the other hand, is a variant of Salsa20 designed for key derivation. Okay. At least if you believe ChatGPT is for key derivation. I guess we just H-Salsa20 uses a longer nonce. H-Salsa20 produces a 256-bit subkey from the given key and nonce. And Salsa20 produces a key stream for encryption/decryption. Cool. All right. So that's Salsa20. What else do we have here? H-Chacha. I'm going to guess that this is the H version of Chacha. And we have more standard operations. We have these, the loading. Here we see the quarter rounds. This is kind of a nicer presentation. And the stores again. And if you want to be meticulous, you can verify that all of these, the combinatorics are where they should correctly be. The quarter round has this ROTL. So when you call quarter round, We're going to add A to B. A equals B. D is equal to RODL32 of D XORed with A 16, and so on and so forth, while 0. Why while 0? Oh, this is because there's some defined trick. I forget. Okay. Here's ED25519. And H2C, I'm not sure what that is. Ristretto. I'm guessing 25519 is the place to be. H2C. So H2C string to hash SHA-256. And what is going on? We're giving it an H, which I guess is the output hash, because the first parameter being the output, the out parameter is the convention so far of this repo. And we, I guess, pass in the hash length. We have some context. I guess that's the message hash so far, the message to hash in the message length. And we start with some state. We create an empty block of hash block bytes long of zeros. And then we have U0 and UX are just kind of being initialized as empty things. I don't know what this T3 is. Some context length thing and some sizes. And we're going to call crypto hash SHA-256 init, and then we're going to call update. So if the context length is big enough, I guess. And something about H2C oversized DST. So I guess this is for handling oversized stuff. And then we're going to call SHA-256 update on passing in ST, which was what? Where did we get ST? I'm not sure. But then we finalize passing in U0. I'm not really sure exactly what's going on here, but this seems to be maybe some condition about the things being longer than the number of bytes that the hash wants to return, perhaps. And if we get down here, then we initialize the hash function. Let's see if I can figure out where ST came from. I think it might be just something that we have access to as part of the class. Oh, no, it's the hash state. Okay, it just starts out as like empty, and then we initialize it, etc. Okay, so we initialize the state. We initialize some empty block. So we update some empty block. I don't know why that's not part of the initialize operation, but I guess it's a thing you have to do. We update it with the message, giving it the message length, and then we update it with whatever T is in 3U. So we're using the SHA-256 thing, and we're doing more than hashing the message. We've got this T stuff, and that's, I think, because that's in service of whatever we're using this hash function for as part of the curve, and updating and finalizing. And then we're going to iterate over the length and do some more hashy stuff. Yeah, I don't know. H2C string to hash. Okay, but let's look at the curve itself. I don't know if I didn't open a header for the curve. Is it just the C file? Okay, so we have this function that will tell us whether an unsigned car is a valid point on the curve. So we've got this GE25519P3. Maybe this is a three-dimensional point. We're including crypto core. Maybe I missed the header because it's an include. I would kind of like to know what kind of object this is. Okay, so it's some struct that has x, y, z, and t. So this is some point on the curve. FE 25519. I don't know what the FE is. To uint 64. Or maybe 5 of them. Okay, so GE. I don't know what GE stands for. Oh, here we go. Representations. This is what I want. GE means group element. Okay. That's extremely useful. That's a little bit, I would never have guessed that, I don't think. So here the group is the set of pairs xy of field elements, satisfying negative x squared plus y squared equals 1 plus d x squared y squared, where d is equal to negative 121,665 over 121,666. And then we have a couple of different representations. So GE25519P2 is the projective representation. It has 3 coordinates, satisfying the constraint that x, that little x equals big X over z, and little y equals big Y over z. So why do that? Well, that way, if you set z to be 1, then you're in a like a patch of the curve where little x and little y are your coordinates. But you might have like a point at infinity or something. And so you might have a place where z is not equal to 1. And you have to have this projective representation. We have the extended representation. I don't know what that's about, but we have now 4 coordinates satisfying x is equal to x over z, y is equal to y over z, and xy is equal to zt. So these two are the same. And now there's this multiplicative constraint that's kind of governed by t. I'm not sure when you would use that, but I'm sure it has a use. Then we have a completed. I don't know what it means by completed, but we have x, z, y, t satisfying x is x over z, y is y over z, y over t. This might be some sort of like compaction or like topological completion. And then we have do if, pre-comp. And the coordinates are x plus z, y minus z, and 2 dxy. Let's see if we can find do if in elliptic curve completion. Now here, speaking about the completion of E along 0, should I think of such a thing as the formal scheme whose underlying topological space is 0 spec R, and whose sheaf of rings is the completion of OE with respect to the ideal sheaf? The formal completion is the... I'm not sure if this is the same notion of completion, but it probably is. That's, I think, mainly going to be about some completion of a proof. Let's see if do if elliptic curve. So there's this Niels do if guy. I think that maybe that's possibly referring to him. Let's ask Gemini and ChatGPT. So explain the coordinate systems here. We'll grab this and send it to Gemini. So it says directly using affine coordinates in computations can be inefficient due to the need for field inversions. So, right, this is affine over some field. I don't know what field we're over. I guess I should have figured that out, huh? Probably F2, I would assume. I mean, what other field do computers work with? ED25519, is that what we are? Is the ED DSA signature scheme using SHA-512 and curve 25519. Okay, so we're in a signature scheme. That's how we were doing all of the hashing. Is ED always a signature scheme? Is this something I've forgotten? Oh yeah, ED-DSA, elliptic Edwards curve digital signature algorithm. Okay. All right, so what I really want to know is about the curve. The curve used is this curve, a Montgomery curve over the prime field defined by the prime number 2 to the 255 minus 19. Hence the numeric 255, 19 in its name. Okay, so the prime number is the field is the field modulo of this prime number, which of course makes so much more sense than the field F2. I think I was thinking of an extension, but that's not how things work. Okay, so this is some number. What makes it a Montgomery curve? I'm not sure. Different from the usual Weierstrass form. I think that's the main form I'm familiar with elliptic curves. And it's defined by some equation. It's considered over a finite field K, for example, et cetera, et cetera. Okay. So we have this curve, and we were learning about the coordinates. So where did the... Here the group is the set of pairs, x, y... Oh, okay. We already read that. All right, so affine coordinates, these... the like 1 over z operation, that requires inverting z in the field that we just saw. And so that says that can be inefficient. So projective coordinates. Oh wait, no. This is just saying the pairs that already satisfy the relationship can be inefficient. So for projective coordinates, the affine coordinates can be recovered from projective coordinates by this division operation. This is useful because it avoids the need for inversion operations in many algorithms. I guess you only really need to invert to recover the original affine coordinates. So we don't need to divide by z as often, I suppose. Extended coordinates. The affine coordinates can be recovered by these things with the additional constraint xy equals et. Extended coordinates are advantageous for certain operations, including point addition and doubling. And then completed coordinates. This is just the equations we saw. This form is typically an intermediate step in algorithms, particularly in point addition and doubling, facilitating efficient transformations. And pre-computed coordinates. These coordinates are often used in optimization techniques, such as windowed scalar multiplications to speed up computations by pre-computing and storing certain values. And so here's the advantages. Extended coordinates simplify. They basically simplify different operations. And completed coordinates are mainly intermediate, it says, and pre-computed coordinates provide pre-computed values to speed up repeated operations. Okay, so that's useful. What's Gemini say? It's saying it's more efficient. Okay, great. So we have these different coordinates. We can convert them to bytes. You can convert between the coordinates. This is just the header, so we don't see the implementation. You can do things like scalar multiply, clear a cofactor, whether the coordinate is canonical, etc., etc. The set of scalars is z, whatever this is. Oh, I guess this is like z mod L. It's supposed to be an L or a 1. L, where L is 2 to the 252 plus this big number. Okay, and so you can invert. This should just be taking modulo the prime. You can negate, reduce, multiply, etc. In fact, let's see if we can find this. Just verify for ourselves that inversion is just modular arithmetic. And I don't know what SC versus FE is, but something. You've got this. Wow, this is pretty involved. I guess whatever this is doing, I'm not sure. We've got SQ, mol. Yeah, I'm not going to track this down. But yeah, no. To invert is much harder. You need to find the number that you multiply it by to get something that's 1 mod the big number, and that is going. You're gonna have to do something. I guess you're gonna have to like do like a GCD calculation, right? So how do you invert a number in a prime field? It's particularly efficient because of special properties of two prime numbers. So we've got the Fermat's theorem. We can keep raising it. You can raise it to the p-1 power. The extended Euclidean algorithm. This is a more general method that can be applied to any two integers, not just elements of a prime field. It involves a series of manipulations to rewrite the greatest common divisor of two numbers, a and p in this case, as one using a linear combination of a and p. And so let's see if this is doing some version of the Euclidean algorithm. I'll say, what is this code doing? So it calculates the multiplicative inverse of a 32-byte element in the field 255 minus 19. It's commonly used. 2 to the 255 minus. Commonly used in elliptic curve cryptography based on blah blah. It declares some large number of 32-byte arrays with names like _10, _100. These arrays likely represent pre-computed constant values used in the inversion process. This approach can improve efficiency by avoiding redundant calculations. Modular exponentiation and multiplication. The core of the algorithm involves several calls to functions like SC25519SQ, presumably for squaring a number modulo the prime, and similarly multiply. Then we have the main loop. It iterates through a series of multiplications, squarings, and multiplications by small constants. These operations manipulate the value of recip array to converge towards the inverse of S. And then after the main loop, there's an additional squaring and multiplications by small constants to fine-tune the accuracy of the inverse in recip. It implements a specific inversion algorithm, likely using a variation of the extended Euclidean algorithm, etc. Okay, so there's some significant, I guess, optimization. And I'll ask ChatGPT. Same thing. Several temporary variables, 32-byte array, and named according to the binary representation of the values they hold, squaring, multiplication, etc., exponentiation, etc., etc. It starts by computing various powers of the input s through a series of squarings and multiplications. For example, underscore 10 is s squared, underscore 11 is s times 10, and so on. And it has some intermediate calculations. But whatever it's doing, it's computing the inverse somehow. And then reducing. So if you give it a thing, it's going to output S mod L. So reduction is the thing that's just modular arithmetic. But it's not just like taking things mod, I guess, because it's not just using like the percent sign. And I'm guessing that's because, first of all, we are stuck with 32-bit arrays. And it's a large prime, and we don't want to overflow. And I guess that's mainly it. All right, so that's the curve implementation. This is the digital signature algorithm. What else can we see before we get to signatures? I don't know what ristretto is. We have KDF, which has the Blake key derivation function, and what's the other one? HKDF. These are classic derivation functions. CryptoKX, this should be extension. This generic hash init stuff, secret key bytes. I'm not sure. Do we get a header? CryptoKX. CryptoKX.h. I'm not sure exactly what's going on, but I'm going to guess that, okay, well, maybe we've got some stuff for CryptoKX client session keys. We're passing in receive. I'm assuming RX and TX are receive and transmit. They each have, they're each arrays according to the session key bytes. Then we have a client public key, a client secret key, and a server public key. And I guess we're like getting another, some more data. CryptoKX. Oh, key exchange. That would make much more sense. So this is key exchange. This is, I don't know if this is literally Diffie-Hellman or what. Using the key exchange API, two parties can securely compute a set of shared keys. See if DH appears anywhere. Is Libsodium's key exchange system secure? 0. Got downvoted. The answer is yes. Is there a formal security definition? How do we know it's secure? Do you get a... Yeah, I don't know. I don't know what... I don't know how to think about this. It doesn't seem to be... So what key exchange algorithm is used by Libsodium? So it says that it uses Diffie-Hellman based on curve 25519. Although Diffie-Hellman doesn't appear to be anywhere in the code, at least not in the documentation. And I don't know how to tell that it's like literally the same. We have one pull request that mentions Diffie. Scalar mult raw. The reason NACL provides this API is to intentionally make it easier to use for the purpose of computing public keys from private keys or performing Diffie-Hellman. The API now makes it quite difficult to do anything wrong and yet still get a correct answer. All right, I'm not sure. I'm going to guess this is, I'm going to guess key exchange is mainly Diffie-Hellman. Maybe there's, maybe Diffie-Hellman technically is based on RSA or something. So it's using, I don't know if this modular arithmetic is part of the definition. Generalization of finite cyclic groups. So it may be this, it may be just a generalization. For example, elliptic curve Diffie-Hellman. ECDH. Yeah, I forgot about ECDH. Let's see if ECDH appears. It's referenced here. I'm not sure. I really don't know. I don't know why they wouldn't just come out and say it if it was the standard ECDH, but who knows? Not me. Here's crypto hash. Should we just take a quick look at SHA-256? We're going to just return crypto hash, SHA-256 bytes. We're including crypto hash SHA-256.h. So there's all the action in the header, whatever key CP is. Colin Percival. So maybe this is the somebody else's implementation of SHA-256. And something like that's going on. I'm not sure. I'm going to stop in just a few minutes. Let me see if there's anything else that I really want to see before. I mean, we could look at a quick KDF. Return context bytes. Int crypto KDF Blake2 derived from key. So I think you get out the subkey and you pass in the subkey length, I assume, and you pass in the subkey ID and the context and the key. And you're going to derive another key. It's key derivation. So we've got this. We're going to create a thing for padded context and a salt. And we're going to use memcopy to copy the context into the padded and then set the remaining memory to, I guess, 0. And then whatever the store LE is, maybe LE is endianness, big versus little, maybe store 64 little endian salt subkey ID. I guess storing the subkey ID into the salt. And then we're taking everything that's not the subkey ID, setting it to 0. And then we do like a verification on the size, and then we call crypto generic hash Blake 2B salt personal, and just our hashing. The thing that we're hashing depends on the context, the salt, and the key bytes. And then as we change the context and I guess really the context and the subkey ID, we get more and more keys. And I think that I'm just about to leave it there. And Elsie, hey Elsie. I can't seem to watch the beginning of those. And I'm still catching up on an Evergroom. Hey, thanks, man. I really appreciate it. Having a backlog is kind of a drag because I feel like it takes a while to edit them all, and then I post them all, and it's kind of hard to follow along. But I really appreciate really appreciate you coming back. And yes, so papers we will get to soon. Soon. There's a little bit. I take a look at a paper kind of totally unprepared in the Stable Diffusion video, mostly because I can't figure out all the stuff that I need from the code. But we're going to do some papers. We're going to do some machine learning papers, which is not my field. We're going to do other papers as well. All right, great. I really appreciate it. So that's all for me for today. Oh wait, yeah. So Clojure is on there. These are all great ideas. You're on the Discord, right? Can you pop them into the Discord, and we'll make sure that we have you should, first of all, everyone watching should join the Discord. And on the Discord, I'm not taking requests yet. I want to get through this backlog first of things that I've promised to do. And once the backlog is done, I will open up requests again, and we'll have a structure for deciding what gets done and when, and that will be to a significant extent community driven. But what I am doing is I'm tracking requests that or ideas that brainstorming ideas that people have, just so that we have them in one place. And that's being tracked on a Google Doc that's available to you if you join the Discord. So if you want to recommend something, that's the place to do it. Also, tell your friends about this channel if you like what I'm doing. That helps out a lot. And I'm going to leave it off there. That is Libsodium. It's kind of a cool project. With the crypto stuff, it's hard to read the code because something like AES, the whole point of crypto is there's all this mixing and diffusion, and you're taking information and kind of swirling it around like you would swirl a cup of paint, and everything's kind of getting mixed up. But what you can't do with the cup of paint, and you can do with crypto, is if you know exactly how you swirled it, then you can unswirl it. And all of the most obvious ways of swirling something up, those got worked out in like the 70s or so. And there's been an arms race for people who are really good at unswirling and people who are really good at swirling. And so over time, things have gotten pretty complicated. One of the things that I think Dan Bernstein, I think it's Bernstein, I always call him DJB, maybe it's Bernstein, I don't know, has done is that there's a real elegance and I think simplicity to a lot of his work. And that was shining through to me. I don't think it necessarily did a good job of making that shine through to you, the viewer. But I think that's really cool. The other thing that's hard about the crypto algorithms is you want them to be fast. So often they're written in plain C, and they're often doing things like working with raw pointers. So it can be really hard to figure out if you have a bug there. And also, like, straight C is not the most readable thing in the world because you have less typing information than you would have with a more structured approach, like like with like modern C++ or Rust or some other language where types are really a big part of the ecosystem and the lifestyle. So that's Libsodium. That's all for me. Thanks for watching.